Hello and welcome to this video where we'll go into the different keys in RDBMS. So here there are several different types of keys, but we will elaborate on what they are and which ones are the most important ones when you're designing your data modeling. Okay, so let's go on to the keynote now. So I'm here in the keynote using different keys in database to identify rows, ensure data integrity, and enforce relationship between tables. Okay, so all of this can be achieved through keys. Cool. So let's go on and see what keys we have. So identifying primary key in this Pokemon table. So we'll take a Pokemon as example. So in Pokemon, you should know that there's an index for each Pokemon that is used in the TV series, it's used in the manga, it's used in the card games. It's called Pokédex. So this is an actual index that exists. So this is not just that we have created this for this database table, okay? And then here in this table, the Pokemon table, we have Pokédex and we have the name. So these are the two attributes we have here. So this Pokédex is a unique identifier for the row. So that means that if I pick Dex number 1, I always get Bulbasaur. Pokédex number 2, I will get Venusaur, and 2 is Ivysaur and 3 is Venusaur. And then 4 is Charmander. Yes, and this Pokemon table don't have all of the Pokemons, of course. So this is just a few of them. And let's check this out. So name, you might think that it also considered unique here. So, but some newer versions of Pokemon, there exists actually something called regional Pokemon. So, for example, Meowth, the Pokemon Meowth, there's a regional version of it that looks really different. And they share the same name, but they have another region as well. So then probably we should have a region here also for modeling. So then by following these business rules, then the name cannot be considered unique here, and it cannot be considered as a key. So, however, Pokédex is very stable and don't change over time. Hence, it's chosen as a primary key. So it doesn't change over time. So it means that even when we go a lot of generations, we still have the rule that the Pokédex number 1 will always correspond to Bulbasaur, right? So the Pokédex number, it is stable over time, unless there might be some rule I'm not aware of. I just followed Pokemon for the first generation. I followed it quite tightly when I was young, and then the second and third, I followed it somewhat, not very much. And then it's still going on now, so maybe this has been changed, I'm not sure. Okay, so Pokédex is chosen as a primary key, and this primary key is a column or a combination of columns to uniquely identify each row. Okay, it uniquely identifies the row. So for example, if 25, then it will be Pikachu here. We won't have another Pokédex that is number 25, because we have uniquely identified that row with the number 25. And also this key is a natural key, because this key exists in the real world or in the business, in the actual application, right? So it exists in the world of Pokemons. It's not something that we make up just for the database sake. So here we move on to candidate keys. They are a set of keys from which primary key can be chosen. So if we follow the same table here, if there wasn't any regional Pokemons, then both name and Pokédex would be considered as candidate key. And then from this set of candidate keys, we pick one that is the primary key. So candidate keys must have uniqueness over time. That's why the name is not a candidate key now. And candidate keys that are not chosen as primary key is called alternate keys. So you choose one that is as a primary key, and then the other ones are considered as alternate keys. And these can be used for some database performance optimization. So, and moving on, we have natural and surrogate keys. So this is a Pokemon type table. And this is the Pokemon table. So Pokédex can be considered a natural key, as it is a unique key that exists outside of the database. So it exists outside of the database, so it's a natural key. However, type ID, it doesn't exist outside of the database because we refer to these types by grass, poison, fire, water, electric, and so on. So this key here, this primary key type ID, it's called a surrogate key, as it has no meaning outside of the database. So we have created it just for having a primary key that uniquely identifies each row. So the type ID is a surrogate key. And surrogate keys can also be created based on other attributes using hashing. And more on this we will come to in the data warehouse course, where we'll come into DBT. And then you will use hashing to base on several existing columns to create a unique hash, which will be used as a primary key. We don't need to care about that right now. Instead, just know that, okay, surrogate keys, it doesn't have any meaning outside of the database, while natural key, it does have a meaning. So the advantage of using a natural key is that you don't need to store as much of data. You don't need to have an extra column for a surrogate key. However, there's a risk on doing that. The risk is that it's very hard to find a primary key, a suitable primary key, that you need to find something that is stable over time, right? So we have different data models for this Pokemon example. So we're starting with the conceptual data model. So you have the Pokemon, you have Pokemon type, and you have type to Pokemon type. And you see one-to-many and one-to-many. So we don't have a many-to-many from Pokemon to type, right? And then you have a logical data model. And the logical data model, we get the attributes as well. And as we know from the previous video, is that the logical model is a more specialized model, because now this is specialized for this particular type of application, while the conceptual model is more general. And here's another terminology which we used before as well, and they are parents, because the Pokemon type, it depends on the Pokemon and the type, right? So this is the child entity. So, and the child entity, it depends on the parent. And then we go into the physical data model, and the physical data model, we also add the domain constraints. So what are the differences between these data models? Actually, I've said it already, but it's good for you to say it also, so that you practice. So I will leave that for you. And then, keeping these models in mind, we will have the tables after we have implemented, right? So we implement the tables, and then we insert data into the tables. And going into the tables, we have Pokemon instance, we have the Pokemon type instance, and we have the type instance. So the difference now is that we have the tables based on the data modeling, right? So what instances mean is that we have a snapshot of a table at a given time. So at this snapshot, we have these rows or these tuples. But in another snapshot, we may have other tuples or other rows, right? These are just instances right now then. And we have Pokédex is the index, right? Or it's a foreign key. And you can see the foreign key, it can have duplicate here. So we can have several Pokédex. Why is that? Well, that is because we have two Pokemon. We have Bulbasaur. It's related to, it's both grass and poison. So we cannot have both of them in one table, right? We cannot have poison / grass, because it has several types. But then we have this Pokemon type instance to keep track of that. So we can have duplicate foreign keys. However, the Pokédex, which is the primary key in this parent table, is unique, right? We cannot have duplicates there. So this is the foreign key, and this is the relationship to it links to the Pokédex primary key in the Pokemon instance. And the type ID, it links to this type ID in the type instance or the type table. And foreign keys, it appears in the many side of the entities. Remember that we had many sides here in the Pokemon type. So we had many from the Pokemon instance. We had one to many, and from the type instance to Pokemon type, we have one to many. So the many side, we have the foreign keys. And they refer to the primary keys in the other tables. And foreign keys, they enforce something called referential integrity, which prevents orphaned records. And what does this mean? Well, it means like this. We will go in here. So it enforces referential integrity. This means that the database, it restricts insertion of row with Pokédex or type ID that don't exist in their parent table. So here, if I would like to add Pokédex number 38, we can't do that because we don't have a 38 here. We cannot have an orphaned child, right? It has to have a parent that it can refer to. So when we try to do this, we will get an error, and so that's good. And also, when we try to delete something, so normal deletion of a row in a parent table that has related entry in child table is not allowed. So when normal deletion is called on delete restrict, we cannot do that. For example, a normal deletion of a row in a parent table. I want to delete number 1 here. That is not allowed because here we refer to number 1. However, when we do on delete cascade, we automatically deletes dependent rows on child table. So if we do on delete cascade on 1, then these 2 rows will disappear as well. This keeps the data integrity. We have referential integrity. Thanks to the foreign keys, we make sure that the sum operations are not allowed so that we keep the reference still active and valid. And here's another example for foreign key, but this foreign key can reference its own table. So you don't need to reference primary key in other tables. Consider this relation here. We have employee. It's the table name or relation name. You can write it like this. And it has an employee ID, first name, last name, and manager ID. So this is a hierarchical structure. I'll show you why. So this is the primary key. So manager is also an employee. So it is in the employee table. Foreign key that references employee ID in the same table, it is a self-referential relationship. And this creates a hierarchical structure. So each employee has a manager, right? And the managers could be employees as well. So let's move on to the last slide here, and we're going into properties of primary key and foreign keys. So primary key, we have it uniquely identifies each row. We have uniqueness, which means that no 2 rows can have same primary key. And it's non-null, so you can't have null in primary key. And there's stability over time, so the primary key won't change. Either it's a natural key or it's a surrogate key. It won't change. It will still uniquely identify each row. So foreign key, it establishes a link between tables. So between 2 tables, you have foreign key to link them, and the foreign key always appear in the many side when it comes to one to many, right? One to many relations. If it comes to one relation, then of course it's not in the many side. Then either side is possible. But yeah. And referential integrity, so that there are some rules about the insertion and deletion. So it ensures the foreign key value must exist in the referenced table. And it can have duplicates, as we saw before, and it can also have nulls. And nulls means the value is unknown. So that is possible. Okay. Okay, so with this, you've seen the lecture about different keys in RDBMS, and there are more keys such as intelligent keys, super key, and some other keys, but we haven't covered them all. Instead, we've chosen some that are more common so that you get a feel about how they work and how they can later on be implemented into the database. So I hope you found this video helpful. Thank you for watching this video. See you in the next one. Bye.